So we'll be looking today at doing calculation questions with regards to magnetic forces on wires or loops. The questions we'll be looking at today are relatively more complex, so you can expect them to be towards the harder end of the paper, although they can definitely still be part of the paper as well, but towards the harder end. So we'll start with this question, and we can examine from our diagram that we've got a fixed wire with 5 amps going through it. And you've got this rectangular loop of dimensions 6 centimeters by 20 centimeters, which is closest side is 4 centimeters away, and it's carrying a current of 3 amps. The question asks us to determine the net force on the loop from the current in the fixed wire. Now, for us to deal with this question properly and be able to talk about it a bit more sort of easily, let's label this loop ABCD. Now, when we are trying to determine the net force on the loop, what that really then means, of course, is then the net force is going to equal the sum of all forces. Now, the loop is made up of your different sides, AB, BC, CD, and DA. So if any of the sides experience a force, then the sum of those forces will give you your net force. So let's consider each one individually. Now, force AB may or may not experience a force. B, C, CD, any of these loops may or may not experience a force, but we need to think of why it would experience a force. Now, it's going to get it from the fixed wire. Now, we know from our theory that if you've got wires that are parallel, then they will attract, and we could just do that. But let's explain that a little bit as we do it as well. This fixed wire has a current going through the right. So with your right-hand grip rule, that means you're going to get a magnetic field going into the page over here. So this magnetic field is not uniform, but there will be a magnetic field into the page. So, and out of the page, all right, up there, not relevant for our question here. But basically, this wire will create a magnetic field. This magnetic field will interact with this to cause you to experience a force. So in actual fact, all sides AB, BC, CD, and DA will experience forces. But more importantly for us is the sides AB and CD. AB is going to the right in the terms of the current. The wire is going to the right, so this is a force of attraction. Now, the current is going to the right like so, but that means it's flowing around like this, which means CD is going to the left, which is opposite to the direction of the wire in the wire, to the current in the wire, which means because opposite ones will repel, this means we'll get a force of repulsion. So I'll call this a force downward, and I'll call this a force upward as far as the direction goes. Now, we haven't really been doing any forces of wires that are perpendicular to each other, but just a quick side note here, BC is carrying current, and it is in a magnetic field, even though it's perpendicular to that wire and not parallel. So if you've got a current going down, and it's in a magnetic field going to the right, even if it's not perpendicular, then it will actually experience a force to the right. And DA, with a current going up and a magnetic field going into the page, it will experience a force to the left. Both of these are opposite sides of the rectangle. One's going to the right, one's going to the left. They'll have all the same parameters. They're in the same magnetic field. They follow the same variation and so on and so on and so on. So we don't need to worry too much about those two. I'm not ignoring them, but actually I don't need to worry about them because they'll cancel each other out. So more importantly for me, I really just need to focus on these two. Now the formula that's relevant is F over L equals K I1 I2 over D. Now for AB, well, that means of course I rearrange to get the force. That means it's K I1 I2 times L over D. We know what K is. K is 2 times 10 to the negative 7. You can look that up. But for AB, we're going to get I1 equals 5 amps, let's say for the wire here. I2 will be 3 amps. And in fact, that's going to be the same for both of them. Now, L is the length of the wire that is parallel. So for AB, that's going to be 20 centimeters, which is 0.2 meters. And D is how far AB is from the wire, which is 4 centimeters, which is 0.04 meters. So we can quite easily work out the force on AB. The force on AB, of course, is going to be your 2 times 10 to the negative 7 for K, times I1, times I2, times L, all over your D. That gives us an answer of 1.5 times 10 to the negative 5 newtons. And remember, we already said it was upward. Now, we can do the same thing with CD. It will still get the same I1, I2, L, except for CD, we're going to get a different L, or different D, I should say, because it's going to be 4 centimeters plus 6 centimeters, which is 10 centimeters, which of course is going to be 0.1 meters. That gives us an answer of 6 times 10 to the negative 6, downward. All right. So at this point in time, we've worked out some answers. We've got one is 6 times 10 to the negative 6 newtons. One is 1.5 times 10 to the negative 5. So then you can now basically think of it in terms of your free body diagram. You've got a object. Upward force was 1.5 times 10 to the negative 5 newtons. Downward force is 6.0 times 10 to the negative 6 newtons. So the net force is going to be, of course, 1.5 times 10 to the negative 5 minus 6.0 times 10 to the negative 6. And that will just be 9.0 times 10 to the negative 6 newtons upward. And that would be your answer to this question. So just recapping, looking at this question, you've got a loop and you've got 4 sides. They actually all experience a force, but it's the top and bottom that matter most. To get the net force, you work out each force individually using a formula, subbing in appropriate values. And once you've done that, treat it like a force analysis question, and then you've got that. Now we'll also do an extension question. So in this extension question here, it's basically the same scenario as we did before, but I've got rid of the numbers because I don't want to focus too much on the actual numbers here. Just want to focus on the concept. We can, of course, tweak the numbers to make them more realistic and so forth. But basically, we've got a fixed wire at the top. Okay, the fixed wire is fixed. It's got some current going through it. We've got a loop at the bottom, and it also has a current flowing through it. And we worked out before that that means that this loop has some forces acting on it. Now, I'm going to stress now that this loop is not fixed and it's made of very light. So think infinitely low mass, basically think no mass. It's very flexible. It's not rigid wire. So the wire is very light. It's not rigid and so forth. So describe how, if anything, will happen to the loop's motion or shape. Now, for part A, let's remember what we've worked out already. We've worked out that the net force on the loop is upward in this situation because there's going to be a force of attraction upward on that coil, and there's a force of repulsion, which is lower because it's further away mainly. So that results in a net force ultimately upward. So if the net force is upward, then if the force is large enough, and we're going to assume it is for our purposes, because we said very, very light, although the force is very, very weak. But if the force is large enough, then that means the loop will accelerate upwards. Now, of course, if you wanted to think about this more comprehensively, you'd actually need the actual numbers for the currents, which we have, but you'd also need the numbers for the mass to then see, is it going to overcome friction and so on and so on and so on. We're going to ignore all of that. Basically, the point here is you've got a net force upward, so there is the potential, at least, if there's no friction, for the loop to be attracted upward. Now we'll consider the shape. Well, right now it's a rectangle. Now we have A, B, C, D. And of course, it might move upward. But that's irrelevant to part B. We're not talking about its motion anymore. Now we know AB is being pulled upward. We know CD is being pulled downward, or pushed downward, I should say. But based on the very brief work we talked about before, this current is going to the right, which means it's creating a magnetic field going into the page at this section. With BC having a current downward, this means this actually has a force to the right as well. And that means this has a force also to the left. Now, if you've got a loop that is made up of something rigid, like just a square or something, then sure, it'll get some forces, but nothing will really happen. But now I'm saying that this is very light, flexible, non-rigid wire, which means that these forces can essentially deform the wire. So if you think of what happens, basically, if you have a starting position of like a rectangle, and what you're really doing is you're, well, pulling bits of it out in all sorts of directions, then that would really change what happens, right? If you pull that and pull that and pull that and pull that, then it's going to basically get rounder, right? You're pulling it out. So essentially, we would expect the shape to become rounder. In particular, it won't necessarily be a perfect circle because this one will be pulled more, like they'll pull this part harder than this part always. But the end result is you'll round it out. It might not be a circle, it might not be ellipse, but that basically is the gist that we're getting at in this question. We now take a look at this question. So this question basically has two wires. One wire is fixed. So think of it like it's on the wall with support. One wire is not. This wire is loose. Now, having said that though, there's current flowing through these wires. The loose wire is below the fixed wire, and it's levitating, basically. It's suspended in midair, 16 centimeters away from the fixed wire, which is carrying 64 amps. Now, we know the mass of this wire, the length is 1 meter, and the mass of this wire is 40 grams. And we're asked to calculate the current in the suspended wire. Now, you will probably find that you will get a chance to do similar questions to this in your exam. Maybe in different contexts, but very similar. And you may get them in sort of in experiment questions. But for here, we're just going to find the current. Now you've got your wire. And we need to think of it as a free body diagram. So the wire is going to want to fall because of its weight force. And we can calculate using mg, and we'll calculate that in a moment. But if we're saying that the wire is suspended in midair, then quite clearly that means it's not falling. And if it's not falling, then that means that there's a force upward. The question then you really need to think about is, where is this force coming from? And so this force upward is really a result of the force from the wire above. So it's the magnetic force from the wire above. So we'll need to be able to calculate that force. and we need to calculate the weight. Calculating weight is not very difficult. We know it's mg. We know m is 40 grams, which is of course 0.04 kilograms. And so we can just calculate that. And that gives us an answer of 0.392 newtons. Okay. So we know that there's 0.392 newtons down. So because it's levitating and suspended in midair, we know that this must also equal 0.392 newtons. I mean, it just has to, right? So how do we calculate that force? Well, F over L equals Ki1 I2 over D is the appropriate formula, but we want to get F as a subject. So that means we've got Ki1 I2 times L over D. I1 is just over here, your 64 amps. I2 is what we're trying to work out. So really, we should really be making I2 the subject, I guess. So I2 must equal D times F, right? You move the D across, all over L times K times I1. We know what D is. It's 16 centimeters. It's all the way over here. So that's 0.16 meters. We know D. We know L, because that's 1 meter over here. We know K, it's 2 times 10 to the negative 7. We know F, because we've already worked it out. We know I. So we just really need to put all those numbers in at this point. Make sure you're putting everything in the right units. It's very important. And of course, just make sure when you use your calculator that you're typing in the numbers correctly. And that gives us an answer of 4,900 amperes. So clearly, this probably might not be very feasible, but certainly if you were able to get 4,900 amperes to the second wire, and if a 40-gram wire was able to carry that much current, well, then it would indeed be floating in midair. So questions like this need you to basically consider the forces that act on this wire, in this case, weight and the force. And because of the fact that, well, it's balancing each other out, that's why it's suspended, and that gives you the current that you would need to pass through this wire. And that's how you do this question. So we now want to determine, in this scenario, we've got two wires. They're both carrying current, different amounts of current, 3 amps and 5 amps. They're separated by 20 centimeters. And you want to determine the magnetic field at YA due to YB, at YB due to YA, and then we'll compare the results and then justify if they're the same or different. And then we'll do the same thing again with forces. So let's do this with the magnetic field first. Okay. So we know the magnetic field is calculated using Ki over D. Where of course K is 2 times 10 to the negative 7 times I over D. So the magnetic field at YA due to YB would just be subbing in 2 times 10 to the negative 7 times I, which is 5, due to B over D, which is 0.2. Remember, this is 0.2 meters. So gives you a nice answer of 5 times 10 to the negative 6. Tesla. Now 2, we'll just quickly do this. So what has changed? Well, the only thing that has changed is the current, I guess. Nothing else has changed. So you still have 2 times 10 to the negative 7 times I, in this case 3, divided by 0.2. And this now gives you 3 times 10 to the negative 6. So the two numbers are clearly different. And so they ask us to compare the result. So we would say quite clearly that the two results are different. The two magnetic fields at the different locations are different. Specifically, one is 5 times 10 to the negative 6 and one is 3 times 10 to the negative 6. In other words, the magnetic field at YA due to YB is stronger than the magnetic field at YB due to YA. And the reason is quite simple. The reason is because they're created by different wires carrying different currents. So we would, of course, write the complete answer out. But essentially, what we really need to focus on is the magnetic field is dependent on the current and the distance. The distances are the same, but the current is different. So in addition to everything we said, we would firstly identify the results are different. We'd explain that the magnetic field at YA due to YB is greater and stronger than the magnetic field at YB due to YA. And the reason for that is because they have different currents, but the same distances. The next thing we'll need to do is consider the forces for YA and B. Well, we could, of course, use the F over L equals K I1 I2 over D. Or if you like, we could sort of do it more fundamentally and do it as F equals BIL. So if you're doing part one, if you're doing the force on YA due to the magnetic field created by YB, then the force on Y1 is going to be the magnetic field experienced by YA, which is 5 times 10 to the negative 6, times the current of YA, which is 3, times the length. We'll just basically call these 1 meter each, right? We'll just take 1 meter section. And that's going to be 1.5 times 10 to the negative 5 newtons to the right. The second force is the wire force on YB. Well, of course, that's going to be YB, where the magnetic field YB experiences, which of course is part 2. So it's 3 times 10 to the negative 6 times the current, which is 5, times 1, which again, of course, is 1.5 times 10 to the negative 5 newtons. And this will be to the left. Now that we're comparing the result, you can quite clearly see that the numbers are the same. So importantly, the forces are equal in magnitude. But a comparison of forces would also, being a vector, needs to also compare the direction. And we'll note that the direction is different. So you could have worked on the direction basically by using a right-hand palm rule, but basically opposite in direction. So they are equal in magnitude but opposite in direction, and we now need to actually justify this. And the justification is quite simple. They are equal in magnitude but opposite in direction, and this is basically because of Newton's third law. The force on Y2 from Y1 must equal to the force on Y2 from the force on Y1 from Y2 must equal the force on Y2 from Y1, same magnitude, opposite direction. And that will be your justification. Now, taking a look at this question may be a little bit more challenging in terms of there's going to be more steps involved, but the ultimate way we're going to do it is still ultimately the same. So let's take a look at what this question is saying. This question says we have 3 wires. They're arranged in an equilateral triangle configuration, which means all angles are 60 degrees. They're all equidistant from each other, and it's a distance of 4 centimeters. And everything is the same. All wires have a current of 10 amps. So this is 10 amps, 10 amps, 10 amps. The direction in this case is different though. That's out of the page, into the page. And we want to work out the force on YA due to the currents in wires B and C. So here's the general gist behind the question. YB creates a magnetic field. It's got a current going out of the page. Use your right-hand grip rule, and it's basically going to create a magnetic field this way. Right? It's going to be circular. So at some point, it's going to create a circular magnetic field at A. And more importantly, at A, that means the direction of the magnetic field from B is going to be tangential. So it's going to be, well, 90 degrees to this directed line. Okay. Probably draw that more like 90 degrees there. So you're going to get some magnetic field in that direction. Now, C is going to be very similar, of course. C is going into the page, which means that the magnetic field lines going around C, I'll use red to show this one, will be going in this direction because it's going into the page. So that means it's going to very similarly create a magnetic field in a particular direction at A. That particular direction more specifically will be, again, perpendicular to this angle here. And so what that really then means is to work out the force on YA, which of course it will because it's got inner magnetic field and it's carrying current, we firstly need to work out the magnetic field at YA. And the way we'll need to do that is we need to firstly work out the magnetic field from YB and the magnetic field from YC and add them together. So that's our first step here. So the magnetic field from a wire is Ki over D. We're going to be examining at YA from B. So we know the distances in all cases is 4 centimeters, which is 0.04 meters. We know the current in both cases, again, is 10 amps. So that makes it a bit easier. So in terms of the magnitude, that's just going to be 2 times 10 to the negative 7 times 10 divided by 0.04. So we're going to agree that it's going to be 5 times 10 to the negative 5 Tesla. So from YB, it's going to be 5 times 10 to the negative 5 Tesla by subbing in the numbers, right? Noting, of course, K equals 2 times 10 to the negative 7. I will leave the calculation as an exercise for you guys. Okay. So with those numbers put in, we get the B. Now, importantly, we now need to add this up. So we're saying we've got B in this direction, which is 5 times 10 to the negative 5. And let's just draw it in our triangle. So we've got a triangle kind of like this. And we know that that's 60 degrees. We know that this is 60 degrees. We know that this is 60 degrees, but we do know that this is 90 degrees to that. And we, of course, know that we also need this one, which is, I probably should have drawn this a little bit better. Maybe let's make that a bit smaller. So that looks a little bit better. Okay, so what we're really doing is we're trying to get the sum of those two, recognizing both of them actually are 5 times 10 to the negative 5. Well, it's not too bad we just need to work on an angle, because maybe you can see from the diagram here that if they're both 5 times 10 to the negative 5, then there's an upward component and a component to the right. There's an upward component and a component to the left. Probably without too much convincing, you can see that the left and the right will cancel each other out, and you'll just get this up. Now, really, we just need to work at an angle. If this is 60 degrees and this is 90 and this is 90, then this is going to be 120 degrees, which means that this angle here will be 60 degrees and this is 90 and this is 30. Okay, just a bit of geometry, right? 360 minus 90 minus 90 minus 60 gives you 120, and these two angles will be equal, right? So because it's all symmetrical. So at the end of all of this, we can then basically work out this component and this component. We're not really going to bother working out this component because we can see that those two end up equaling. But importantly, this component will be 5 times 10 to the negative 5 times cosine of 60, if we're using 60 degrees, which is going to be 2.5 times 10 to the negative 5 Tesla. In my direction, upward here. That's one of the components, of course. And therefore, the sum of the blue and the red will be, well, of the blue plus the red, basically the two magnetic fields, will equal 2.5 times 10 to the negative 5 times 2, which is 5.0 times 10 to the negative 5 Tesla upward. So that gets me something I need to answer this question. I've now got the magnetic field. That's at A. I haven't yet found the force, but that should be pretty easy now. Because at this point in time, I will simply use the appropriate formula. So as from A's perspective, we know the magnetic field strength is 5 times 10 to the negative 5 Tesla. It's carrying a current of 10 amps. Now, interestingly enough, we don't actually know the length of these. So we can't really work out the force. This must mean force per unit length. So unless I know the length of A, which we don't, this really means force per unit length. So that means I have to work out basically, well, F equals BIL. It's all perpendicular, so I don't need to worry about sine theta. So F over L equals BI, which is 5 times 10 to the negative 5 times 10, which is 5 times 10 to the negative 4 Newton per meter. And that would be your answer. This is force on A due to B and C. Force per unit length. And so this would be your answer here. 5 times 10 to the negative 4 Newton per meter. Of course, as an exercise, you could redo this question with a specific length for A, B, and C. You could also work out the force on B due to A and C, and the force on C due to A and B. I'll leave that as an exercise for you guys to do. But that's basically how you would do it. You will work out the magnetic field, keeping in mind the geometry that it's circular, so it's tangential. Once you've separated, worked out the magnitude that we did before, then worked out the directions, then you'd add them up to get the final net magnetic field at that point, and then just use F equals BIL here.